Good morning. Happy Friday. I hope your day is going well, and I hope your weekend is even better. Monday, 1:10 p.m. for everybody in this room. We'll not do problem set 4 and quiz 4, but we'll take the first midterm, which is what we're doing all these review sessions for. And when you come on Monday at 1:10, definitely to the midterm, you can absolutely have a note sheet, single page, double-sided, 8.5 by 11. Anything handwritten is fine, but nothing computer-generated, scanned, that kind of jazz. You can also have a periodic table. Definitely bring your calculator. Good to go. You'll also bring the acid and base titration lab that we did this week, and exam prep 1 worksheet will be happening. Most of you have seen these before, but in case you haven't or you don't remember what you had for breakfast this morning, an exam prep is usually about 5 questions, and the questions have the answer. And your goal is just to show how you go from the question to the answer. So show like detailed steps, all right? Don't just like, oh yeah, this and stuff. Show me how you'd set it up, and if you have to calculate numbers in between, that kind of jazz. Should be pretty chill. We will also do the titration of weak acids lab afterwards. It's very similar to the acid and base titration lab, but you'll actually analyze a weak acid, finding its Ka, its molar mass, and stuff like that. It should be too big of a deal. When you get your midterm back, you'll get a summary sheet that'll say how you're doing in the class as of this time. If it says that you're missing a lab, boy, make sure you get that into me. Very, very important. Also make sure, of course, that the scores I have are the scores you actually got, stuff like that. I definitely recommend that you look at the sample midterm, which is in the companion and online. It'll give you a good sense for the kind of questions I'm looking for. You can probably gather where some of the questions will be, but that's going to give you a good idea like how it is. Any questions? That kind of stuff. So what we're doing is we're just going through some questions and stuff, trying to figure out how this all puts together. This is a question that I showed at the end on Wednesday, and there's a couple ways to do it. You can do it the math way, which is fantastic, but you can also, if you think about what it means to have a pH of an acid and a base, hydronium and hydroxide, I think you can figure it out without doing any math. So see if you can figure this out. In a few minutes after you've had a chance to think about it, I'll talk about the answer. Cool. So let's talk about the math way to solve this first, and then I'll share with you some ideas about how you don't need to use math if you don't want to on this problem. If you use math, we look at sodium carbonate, and you may not know a lot about sodium carbonate, but notice that it has a Kb, all right? Does that mean that this is going to be acidic, basic, or more information?
Basic.
Basic, that's right. B means base, all right? Ka means acid, Kb means base. And because there's a K, is that going to be a strong base or a weak base?
It's going to be a weak base.
Weak base, well done. K's less than 1 are always weak, okay? And honestly, the strong bases don't have a meaningful K to use. So all KBs that are less than 1, which is basically all we're going to see, those are all going to be weak bases. So the math way of doing this, weak base, 14 plus log square root of KB times CB. And you've got the KB value. You've got the CB, the concentration of your base, 0.15, and you can plug it in to find the pH, the far right column. From there, hydronium would be 10 raised to the power of minus pH, and finally hydroxide would be Kw, the only K that you need to know for Monday, divided by hydronium. What's the value of Kw?
10 to 14.
10 to the minus 14th, well done. So this is a cool way to do this problem, absolutely. But if you want to be kind of tricky about it, if it's a base, what range of pHs would you expect to have?
Between 7 to 14.
7 to 14, above 7, something like that. Yeah, that's right. So would it be reasonable to have a pH of 5.61? No. So A and D, we would not expect to be meaningful here because it's a base, all right? Bases have basic pH. So then that leaves us B and C, all right? Well, same number, so we have to look over here. Do bases have more hydronium or more hydroxide? Hydroxide, you bet. This number, 10 to the minus 3, is a heck of a lot bigger than 10 to the minus 12. Down here, the hydroxide, 10 to the minus 12, would be smaller than the hydronium. But here, the hydroxide is certainly bigger than that one. So without doing any math, I would think that answer B would make sense, all right? Now, if you want to do the math, which is the ultimate way to do this, you will find that answer B is correct. So here's 14 plus log square root KB times CB. I got the 11.75 pH value. Hydronium 10 raised to the power of minus 11.75 comes out to be that. And then Kw, the only K that you need to know on Monday, 10 to the minus 14, divided by hydronium will give you hydroxide. And you could go, by the way, pH to POH and hydroxide 10 to the minus pH. That's fine too, but minus POH, excuse me. Cool. So if you can think about what it means to be acid and base in terms of pH, hydronium versus hydroxide, you're good to go. And again, the punchline here, pHs will be greater than 7 for bases, less than 7 for acids. And when it comes to hydronium hydroxide, bases have more hydroxide and less hydronium. Acids would be the opposite, more hydronium, less hydroxide, but they're all limited by Kw at room temperature. Questions on that? Cool. All right, here we've got a bunch of acids, and we've got their pKa's. And the question is, put these acids in order of increasing acid strength, all right? So we want the weakest acid first and the strongest acid last. See if you can do that based on those pKa's. And again, there's a couple ways to do this problem.
8. It was 8 point something to 11 point something.
That's stupid.
Mine's that.
Okay, so yours was right, mine's wrong.
The second question. So, you do the null.
Yeah.
Did you do like mu1 minus mu2 equals 0?
No, I always do. You really do.
That's what I did. Oh,
It's just, he fixed the math. He did credit on that. It's just the online thing's so strict that that's what he goes back and Jeff says. I'm being this is 2, so 7.
So all weak acids, HA, are in an equilibrium with water. They make the conjugate base and they make hydronium. Now, when chemists talk about the strength of acids, which of these species are they looking at? Hydronium, H3O plus. Good, I like all these answers and stuff. Yeah. The more H3O plus, the stronger the acid. The less H3O plus, the weaker the acid. So when when chemists talk about strengths of acids, you always look at how much H3O plus is created. Now, if H3O plus gets bigger, does that make your Ka number get bigger or smaller? Bigger.
Yeah, bigger.
Yeah,
So
that's
it's
right.
because if the bottom's not growing, yeah.
You bet. That's right. They're right across from each other. So as hydronium gets bigger, your Ka gets bigger. So one of the problems we looked at in problem set 2 was talking about the strengths of acids, which way the directions go. It's always the strongest goes to the weakest. So the strongest is a good indicator as to where your equilibrium lies. So the more hydronium, the bigger the Ka, all right? So on these problems, we have pKa. So one way to do this problem is you could figure out the actual Ka values. You'd go 10 raised to the power of minus pKa, and that would give you Ka. And you'd have the different values right there, and that's totally legit to do that. And as you had a bigger Ka, you'd have more hydronium. That would be strongest, smallest Ka, less hydronium. But an even easier way, once you get used to it, good, some of you are seeing it, good. pKa is like pH. So let's say those were not pKas, but they were all pHs. And I said, list them in order of strongest amount of acid to weakest amount of acid or something like that. Well, this would have the least amount of acid because it's the biggest number, all right? That would be more like a basic pH if it was pH. And this would be the most acidic because it's the smallest number. So another way to do this is to realize that you're going to have a bigger, if this was pH, you'd have this would be the most acidic and this would be the least acidic. And you can do it with pKa too, because this number will have the biggest Ka, which will give you the biggest hydronium. And this number will give you the smallest Ka, which would have the least amount of acid. So one way to do this is, if you do it that way, you just want to go from biggest pKa to smallest pKa. And if you do that, you should get answer D. So again, you can do this either actually calculating Kas, and the biggest Ka will have the most hydronium, smallest Ka will have the least one. But if you think about it like acids, that's kind of the way to go here. You don't have to go through the calculations.
So it's just like, wait, didn't the lab just show pKa equals pH? I was just like, wait a second.
At half equivalence, well done. Somebody
Yeah.
was watching the lab, well done. Absolutely. It's a G-rated F word. I think it's G-rated, maybe. Well, anyway. Questions? pKa? Good. Here's a bunch of different compounds. Think about if they are more likely acids or bases in terms of Lewis acid-base theory. The answer is not E, but I do want you to think about which ones could be Lewis acids and Lewis bases.
and then just boron. It's weird. So, I think acid acidic, and then chloride's just weird. Well, it's accepted. I mean, chloride's negative, so it's definitely accepted. Electrons. Yeah, it's taken out. Yes. No, it should be.
Okay, so Lewis acid, Lewis base theory is a little different than Bronsted acid base theory, which is what chemists use most of the time. But in reality, Lewis acid base is a better, more comprehensive theory. So let's talk about it. A Lewis base is an electron pair donator. So if you have a Lewis base, you have to have something that's going to be able to donate electrons. And a Lewis acid is some kind of element with room for lone pairs, all right? And as we talked about in class, the common Lewis acids will be the so-called twisted metals, which is group 3A. So boron, aluminum, gallium, sometimes indium, beryllium sometimes falls in that category, and definitely all the transition metals, lanthanides, and actinides. Now, transition metals, lanthanides, actinides, they get more orbitals than I know what to do with, so there's all kinds of room to store stuff. These elements, the twisted metals, one reason why they're so twisted is if you remember from Chem 222, some compounds could be under an octet, and that was aluminum, boron, beryllium. And aluminum had an empty orbital, boron had an empty orbital, and most of the time it didn't need it. The formal charges were zero, all that kind of jazz. But you can have a Lewis base come up next to it, and those lone pair electrons are pushed into that empty orbital. So if you see this kind of interaction, there's usually like an arrow that points to it, and that says that both electrons are coming from the base to the acid. Now this aluminum chloride bond right here is the traditional chemistry bond. And if I went up to Ollie, you don't have to do it, but I said, "Hey Ollie, what's going on?" I shake your cards. Yeah, shake your head. Yeah, one electron from each atom. That's a normal covalent or ionic bond, all right? These are kind of weird because it would be, don't do anything. It'd be like me coming up to you and saying, "Ollie, I haven't seen you." Some kind of creepy double handshake thing, and I don't want her to feel weird about it, so I wouldn't do it, right? But that's what's happening with Lewis acids, Lewis bases. So when it comes to this list then, if you go through here, boron is a twisted metal, all right? It's always got room for extra things. Boron, aluminum, right there, acids, big time. Anything with lone pairs is going to be potentially a Lewis base. So ammonia, like all nitrogens, phosphoruses, arsenics, they've got lone pairs. They're going to be bases. Chloride could be a base. Oxides will be bases, sulfur, stuff like that. And the other one that could be an acid would be the transition metals. All of the transition metals will have room for these things. In the Le Chatelier's principal lab, those were the complex ions you saw when the zinc hydroxide disappeared. Those were the complex ions because these crazy transition metals, they've got tons of room for extra Lewis bases making these weird ions. So the ultimate answer here would be yes, there's a picture of Public Enemy, all right, Chuck D. Masters in business administration, but not chemistry. There's good old Flavor Flav. I'm kind of embarrassed to know him these days after some of his VH1 things, but anyway, Professor Griff. Anyway, I won't go into their names, but anyway, they're kind of cool. Yeah.
It seems backwards compared to the regular ones because in like the normal acids and bases, like the acids give hydrogens,
Right.
Where the bases give electrons.
Oh, totally.
I always think about the acids give and the bases receive. There's a lot of ways I think about it, but this one's backwards from that.
It is. It's totally backwards. Like you'd think looking at NH3 that this would be more like could have an acid or a base thing, but in this theory, it's all about those crazy lone pairs and stuff. So no, it's weird and stuff.
Flip-flop.
As you go farther in chemistry, this becomes more and more useful. So that's why I'm kind of introducing it and stuff. So, but yeah, it's weird. There's really no H plus, no HCl, no acetic acid and stuff like that. So cool. Any questions?
So if it has a lone pair, then it's a base, and then if it's one of the twisted metals, it's an acid.
Yeah. That would be a cool way to say it. And like chloride absolutely could be a base, but this is the active part here. Those twisted metals do desire to be like tetrahedral, if you will. So if you have one of these, that's the important part to focus on. But yeah, if you're ever uncertain, Nadia, just like if you could draw a Lewis structure, and if the thing has a lone pair on it, which most of them do, you should be good to go. Questions? Okay. Here's a question. We're adding some ammonium chloride to water, all right? And the question is, if you have ammonium chloride in water and you add ammonia to the solution, what will happen to the pH? So think about that, see if you can figure out what's happening here, and we'll talk about it in a little bit. What have I written up here on the chalkboard?
Strong acids.
Strong acids, strong bases, right on. I hope these are getting more and more familiar to you all the time. Why that's important here? Ammonium chloride in water dissociates to ammonium and chloride. And chloride is one of the conjugates of one of the strong acids, strong bases. And all 8 of these, which is one of the reasons also I want you to know these, have no effect on pH, all right? So those are pH boring, I've called them before. They don't do anything. So we don't care at all about the chloride, but ammonium is certainly a player, all right? And ammonium is a weak acid. It's different from ammonia, NH3. Ammonium reacts with water to make ammonia, the conjugate base, and hydronium. So knowing that, if you have just ammonium in solution, will this be an acid or a base? Acid. It's creating hydronium, all right? It's not ammonia, all right? Ammonium has this extra hydrogen on it, and it kicks it over to water to make hydronium. It's going to be an acid. So ammonium chloride in water will be acidic, okay? But honestly, you don't need to know that for this problem. I'm just kind of talking about it to get on my high horse a little bit. I wanted you to think about when things affect pH. But really here, we're adding ammonia. Now, from earlier, ammonia, acid or base? Base. This is the acid, water is the base. It's going to make the conjugate base, and hydronium is the conjugate acid. So it's a base. So pHs, how will they be affected if you add a base?
Increase.
Increase, absolutely. So you are adding a base, all right? Now, here's the Le Chatelier's principal way to think about it. Woohoo! You've got an equilibrium. You're adding a product. Products make reactions go to the opposite side, to the reactant side. Will hydronium go up or down upon adding ammonia? Down, that's right. As the hydronium goes down, hydroxide goes up. Hydroxide is a base, all right? That's another way to think about it here, how the pH should go up upon adding ammonia, all right? So you can either just think about it just basically like, sorry, that was unfair. Sorry. If you add ammonia, thank you for getting it. Ammonia is a base, all right? So you add a base, your pH is going to go up. But also, if you have this equilibrium, yeah, you're adding a product, it's going to move to the reactant side. Less hydronium means more hydroxide. Basic. Questions? Cool. Sodium chloride, how will that affect the pH after what we just talked about? What do you think? Not going to affect it. Good. You can put in your answer or just look at it. But yeah, again, this magic list. I'm going to keep talking about strong acids and strong bases. Well, after next week I won't, but this week I will. All right. And check this out. Sodium chloride. Sodium is the conjugate of sodium hydroxide, and chloride is the conjugate of HCl. No effect. Any combination of the pieces I've circled up there will not affect your pH, all right? So potassium nitrate, no effect, all right? Lithium perchlorate, lithium bromide, no effect, all right? It's a cool list to know for multiple reasons and stuff, so. Their conjugates are strong acids and strong bases, or strong bases and strong acids, so there's just no way that they can fight back. Questions? Which one of those would be an ideal buffer solution? See if you can figure it out. We'll talk about it here in a little bit. Buffers are amazing because it allows an acid and a base to coexist in the same solution. And these 8, again, strong acid, strong base. You're so sick of me talking about them. I'm sick of talking about it myself to a point. But anyway, these are like the Terminators, all right? You know, they're kill or be killed. They don't stop. They keep coming after you, all this stuff. All right, bad movie references again, sorry. But anyway, they're very, very product favored. We use single arrows with them. So you can't have a buffer with any of these, all right? They're just too strong. But if you have, for example, ammonium is a weak acid. Ammonium can coexist with ammonia. So we've talked about Kas and equilibrium constants. They're less than 1, but that also means because they're less than 1 that nothing is 0, all right? So you have the weak base and the weak acid at the same time. And that's really what a buffer is. So to have a buffer, you have to have 2 things, all right? You have to have conjugates of each other. Let's review that. These 2 are conjugates because they're related by an H+. This one has an extra H+, it's the acid. This is missing an H+ relative to this one, so it's going to be the base. Water and hydronium are conjugates too, although not as exciting. So they have to be conjugates, and the other thing is that you can't have strong acids or strong bases because they don't have this nice equilibrium, all right? They're the Terminators. They go one direction. So if you look at these combinations, the best answer here would be A. HCN is an acid. The H is listed first, but it's not one of the 5 strong acids, so you can assume it's weak. And the K plus is kind of boring. Remember, K plus is one of these guys over here, doesn't affect anything. Cyanide is the conjugate base of HCN. So these are conjugates, weak acid with conjugate base. This has a strong acid and a strong base? No way. This is acetic acid. This is formic acid. 2 acids would be hard to make a buffer from, and they're not conjugates, so that's not a good combination. HCl and Cl minus are conjugates, but again, no strong acids. HCl will just dominate that thing. And methanol and sodium hydroxide, that was just for fun, I guess. So anyway, so conjugates, plus or minus H plus, and they have no strong acids, strong bases. Question? Okay, here's a calculation with a buffer, all right? And in this question, we have ammonia and ammonia. So this reaction I wrote up here is one way to think about this. It's ammonium plus water making ammonia plus hydronium. See if you can find the pH with those kind of conditions up there. Okay, so the traditional way of solving a problem like this is you'd have ammonium plus water making ammonia plus hydronium. I'm using ammonium as the weak acid because we have the Ka. You could do this from ammonia making hydroxide, but with this problem it makes sense to do it this way. So initially, if you have an ice table, initially ammonium 0.20 moles per liter, and ammonia is also 0.20 moles per liter. Now, hydronium is 0, and when you have equilibrium, you can't have 0 or negative of anything. So what that means here is hydronium must increase. So you're going to have X hydronium at the end. You'll have, this one's going to go up too because they're both products. Remember, there's a line of demarcation, and one side will always be positive for X's and the other side will always be negative. So in this case, hydronium has to go up, so that means this one's going to go up, but then the ammonium is going to decrease to make the hydronium. So Ka products over reactants, 0.20 plus X times X divided by 0.20 minus X. Now, as we talked about, if 100 times K is less than C, you can almost always get rid of the plus X minus X kind of things. What would be the number for 100 times KA?
-8.
Excellent. 5.6 times 10 to the minus 8. If you have to do the test, you just add 2 to the exponent, all right? So 100 times Ka would be 5.6 times 10 to the minus 8. And that certainly is smaller than either of these concentrations. So you can pull out the plus X, you can pull out the minus X. X is going to be the Ka times the concentration of the base divided by the acid. That's hydronium. Minus log hydronium, blah, 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 will give you pH. But goodness gracious, I hope that you know by now that I'm in love with the Henderson-Hasselbalch equation. pH equals pKa plus log base over acid. And why I'm proverbially in love with it is because you don't have to go through ice tables and you don't have to think about these things. So base 0.20, acid 0.20, minus log Ka is going to be this one. And even better yet, if the concentrations are equal, which they are here, pH and pKa are the same. So 9.25 is the answer. So either way you do this, full ice table solving for hydronium and then pH, or just using the HH equation, you should find that pH is 9.25. I really think HH is better. Here's the reasons. No ice tables, woohoo! Also, you can use moles per liter over moles per liter, which is what we used here, or moles over moles, all right? Sometimes one is easier than the other. You get to pick. Questions? Here's a buffer, but now we have unequal concentrations, very similar to the last problem. See if you can figure out what the pH will be.
It's too close. Yeah, that makes more sense because there's more ways to put higher. And with the alcohol, how little acid, logic out, that was 9.25, just let this one a slightly It's kind of nice that you can look at a buffer as long as you really keep kind of tell it's not acid. Just by looking at it.
Fantastic. Okay, like before, classic ice table, you're starting with the same amount of ammonium, but now the ammonia is bigger. And I just want to point out once again that even though the ammonia is bigger than the ammonium, again, you can't have anything equal to 0 at equilibrium. So we don't have any hydronium initially. This is still going to go up by plus X. So at equilibrium, this will still be 0.20 minus X because you have to use up some of this to make hydronium. That's going to be X, 0.50 plus X, et cetera, Ka. Again, like before, it's a lot easier to use Henderson-Hasselbalch. pH equals pK plus log base over acid. And we'll talk about the answer in a second. But before we do that, in this problem, relative to the last problem, we have more base now relative to the acid ammonium, all right? And if you have more base, will that make our answer more acidic or more basic?
More basic.
Basic, all right? So if you're feeling confident about this, more base relative to the pKa means that the pH should be more basic. And that's what it is. Don't believe me? Don't worry about it. Plug it into good old Henderson-Hasselbalch. pH equals pKa plus log base over acid, 0.5 over 0.2. And sure enough, it does become more basic. So you can see how this stuff is all pumping together. And that's why I keep going over. You add a base, pH should go up. You add an acid, pH should go down. It applies to buffers. It applies to everything and stuff. So, questions? Sweet. Okay, here's another problem now, but a different buffer system. We have sodium acetate and acetic acid. We have a Ka. In this combination, we want a buffer with a pH of 4. And we have this much acetic acid, and we want to know how much sodium acetate we need to make this pH equal to 4. There's a couple different ways to solve this, all right? I'll talk about it in a little bit. See what you can do here. Remember, this is a little different kind of system than we use. So with the Henderson-Hasselbalch, pH equals pK plus log base over acid. And in the last examples, we used molarity over molarity, which is fine. But you can also do moles over moles. And an extension of that is that, remember from the titration lab, if you have the concentration of what you have and the volume in liters, Moles per liter times liters will give you moles. So another extension of Henderson-Hasselbalch is you can use concentration times volume for moles, all right? And this is just another little trick of the trade. So you don't want to use just concentration because the concentrations are the same and you want a volume, all right? So what I would do in this problem is either solve for moles. You'll solve for moles of weak base, and weak base moles divided by concentration will give you the volume in liters to milliliters. Or you could use concentration times volume for both of those. And if you look at this expression, then you have everything except the volume of the base. It'll come out in liters, turn it into milliliters, stuff like that. Acetic acid is obviously the acid. Acetate, the conjugate base, will be the base. You've got Ka, which you can turn into pKa. Concentrations, both of these will be 0.1, so they cancel out. You have the volume of the weak acid, 0.1 liters. So you really just need to solve for volume of weak base. And if you did all that correctly, it comes out to be 0.018 liters, which would be 18 milliliters. There's the 0.018. So this is another kind of a twist of things you can do. In this case, these concentrations are equal, so you can cancel it out. That's only works, of course, if the concentration is good. The reason I'm bringing this one up is one of the exam prep questions says something about your total volume of a buffer has to be 1 liter. And that means that the volume of the weak acid plus the volume of the weak base is going to equal a liter. So up here then, you could substitute pH equals pKa plus log. You could use concentration of the base times 1 minus VWA, and in the bottom, you'd have VWA. So hint, hint, hint for one of the exam prep questions. If it still is weird, come see me on Monday. We'll talk it out and stuff. So, any questions? All right. Have a great weekend. Thanks for being here. I'll see you on Monday.